Jnanam paramam dhyayam. Knowledge is supreme.
Welcome to this lecture on advanced transition metal organometallic chemistry. As a part of our discussion on CC cross coupling reaction, in the last class we have looked into palladium mediated allylic alkylation reaction, and we had observed that like carbonyl alpha carbonyl alkylation reaction, allylic alkylation reactions are less explored, and we have looked into various mechanistic aspect of this allylic alkylation reaction, and what we had seen that this that the catalytic cycle of allylic alkylation reaction involves a palladium 0 palladium 2 shuttle, and that involves 3 steps, in which the first involves initiates with an oxidative addition state, followed by a sigma pi rearrangement, and then the third step involves the attack of the nucleophile resulting in the allylic nucleophile getting attached to the allylic position along with the regeneration of the palladium 0 species. We have also looked at how the nucleophile really attack, and this was illustrated by looking at a cyclic substrate, for which it was seen that for soft nucleophiles the attack happens at the allylic position from the far end, that is from the extra side. Whereas for hard nucleophiles there is an additional step, and the nucleophile first goes and attack the metal center, followed by an endo attack on the cyclic substrate, resulting in the corresponding product that involves inversion of configuration, whereas for soft nucleophiles it was observed the reverse, that is the retention of configuration. And then we had also taken a look at asymmetric allylic alkylation reaction involving a chiral catalyst, which could give this reaction in very high yield and enantioselectivities. So, with that said, we are going to take up another interesting reaction. This is Hick reaction, and this also involves palladium 2 palladium 0 palladium 2 shuttle, and also gives this CC cross coupled product. So, let us today take a look at this Hick coupling reaction. And this reaction is illustrated by the replacement of vinylic proton vinylic proton by vinyl benzyl or allyl group. And this is shown over here. This vinyl bromide reacting with this ester in presence of base, which is triethylamine, at quite higher temperature 100 degree centigrade, in presence of 1 mole % of palladium acetate, and the ancillary ligand being phosphine, which is in 2 mole %. This is under ligand assisted catalysis condition or LAC condition. And now LAC condition means that the catalyst active species, which is palladium bisphosphine, is formed in situ from the 2 precursors, one that is palladium acetate and palladium and the triphenyl phosphine during the course of the reaction, and then the active species source formed then carries out this catalysis. So, this is called ligand assisted catalysis or under LAC condition. The corresponding the Hick product obviously is the coupling of this aryl vinyl bromide with this vinylic proton, giving rise to the desired product. CO2 Me. Now, one sort of sees that usually this desired product is by and large predominantly trans, and Hick that is one of the hallmark of Hick coupling, that this a trans product is observed. Now, we would sort of start looking at the mechanism, but before we do so, let me just look at the substrate that undergoes this Hick reaction. The substrate which does are these vinyl halide, benzyl halide or aryl halide that adds against the vinylic proton of this activated olefin. So, these vinyl halide or benzyl or aryl groups does not have any beta hydrogen. So, that sort of promotes the reaction in forward direction and not the reverse, that is that in other words to say that this will sort of facilitate the oxidative addition step, the first step, and not the other way around. Now, I am going to illustrate this more with the mechanism that we are going to be discussing, and then we see how this beta hydrogen elimination has been deliberately suppressed in these three substrates, vinyl, benzyl and aryl substrates, such that the Hick coupling proceeds in the forward direction and the reverse reaction of beta hydride elimination for this substrate does not occur. As a result, the coupling reactions proceed as desired. So, I am going to illustrate this more convincingly with this mechanistic cycle, which will show why this substrate does not undergo beta elimination reaction. So, the precatalyst over here is a palladium 2 species, palladium bisacetate, L equals PPH3, X equals halogen in presence of twice L Et3N, giving palladium 0 PD L2 species. Now, this reacts with R dash X and undergoes this oxidative addition. And this R dash X are vinyl, benzyl and aryl group, which does not have beta hydrogens. As a result, the reverse beta hydrogen elimination does not occur, and this give rise to the palladium 2 species R dash. Now, this reacting with this olefin which has a vinylic hydrogen, and this olefin then coordinatively inserts into the palladium R dash bond. This is kind of coordination insertion chemistry going on over here to give the complex which is palladium L R H H R dash. So, this is a coordination insertion into palladium alkyl bond. Now, one thing that one has to remember that these R dash X are the substrates which does not have beta hydrogen. As a result, once the oxidative addition occurs, it cannot decompose through beta hydride elimination mechanism. So, it can only move forward, and when it moves forward, then the olefin undergoes coordination insertion into the palladium R dash bond, and this gives rise to these coordinative insertion reactions of the olefin to these species, which then undergoes beta hydride elimination as shown over here. So, this is the beta hydrogen and this undergoes beta hydride elimination to give this trans olefin, which is a desired Hick product, and this method this step is called beta hydride elimination, and this step is called coordinative insertion of olefin into palladium R bond, palladium alkyl bond. So, once this beta hydride elimination happens, then the desired Hick product along with the formation of palladium hydride is observed. Now, the palladium hydride in presence of base will picks up this proton and halide to give back these palladium 0 species, and this is a stoichiometric reaction. Stoichiometric reaction. So, this is an interesting cycle containing 4 elementary steps. The first obviously involves the formation of palladium 0 species from palladium acetate in presence of phosphine, and then the palladium 0 species then undergoes oxidative addition with R dash X, R dash can be vinyl benzyl aryl group. Once it has undergone oxidative addition, it has become a palladium 2 species. Then the coordinative insertion on the palladium R dash bond with the olefin sort of occurs, coordinative insertion followed by beta hydride elimination, leading to the formation of the desired product, which is the olefin, substituted olefin along with palladium hydride complex, which when treated with triethylamine regenerates back the palladium 0 with the elimination of HCl. So, this is by and large the established mechanism in which this unique cross coupling of in Hick reaction proceeds. So, these coupling reactions has a effect on the counter anion, and the effect of the counter anion is sort of elucidated by the following experiments. So, participation of anionic palladium species in catalytic cycle. And this is sort of illustrated by the following example: twice L plus PD O AC whole 2 in presence of 2 electron and O S minus gives this L 2 PD O AC minus, which then reacts with R dash X to give the oxidative added product R 2 R dash PD X O AC minus, and this emphasizes the influence of anions in the rate of oxidative addition in catalytic cycle. So, this emphasizes the influence of anion in the rate of oxidative addition in the catalytic cycle. So, this is an interesting example. Another seminal study has been done to see the effect of the solvent and how the reaction proceeds in the polar and non-polar medium. Now, this has been examined after the first step, where the oxidative addition reaction has taken place, and that how the solvent influence kicks in over here. So, we are going to see that how the solvent polar P or non-polar N affect the catalytic cycle. So, after the oxidative addition has taken place, the product of the following intermediate has been isolated L L, and this is R X. Now, in presence of non-polar solvent N or non-polar medium, this is in equilibrium with in presence of solvent S, they loses the L, S equals solvent. So, one of these L is lost and then solvent goes and occupies its place to produce this intermediate L P D S X R, and then this further adds to the olefin in presence of solvent to give this product, which is L P D olefin X R. However, the reaction proceeds in a different direction in presence of polar or polar medium, in which this sort of stays undergoes a rearrangement, which is shown over here. From trans it becomes cis, R X now has become cis with L, and then in presence of a solvent S, this X dissociates and solvent goes in to give this product, which is L P D S L R plus and X minus, and that in presence of olefin gives the corresponding product which is L P D olefin R L and X minus and P D plus. So, what we see as seen from the green line over here is that in the polar medium actually it helps dissociate X, and X stays as a counter anion that sort of first gets occupied by the substrate followed by this olefin, whereas in a nonpolar X medium this dissociation of PDX is suppressed as well as X remains, and one of the neutral molecule S is replaced by S followed by the olefin. Now, the subsequent step however is the insertion of this R into this olefin, and that is a concerted mechanism. Olefin insertion occurs in a concerted fashion and is explained in the way as it is shown. P D R olefin, it goes by a transition state which is P D R and then finally going back to P D R. So, this is a concerted process, and what one can see is that this polar pathway has a detrimental effect in regioselectivity. So, what we saw that non-polar versus polar. So, what we saw that polar pathway is detrimental to regioselectivity, and this is illustrated by this beautiful example where the reaction is done after the oxidative addition DPP pH palladium X. So, that means the first oxidative addition has taken place, and then the olefin is kept styrene, and then there are two kinds of product. One is this versus the desired trans carbene. So, what one sees that depending on the X solvent, percent formation of this product, percent formation of this product, what one sees that when X is OTF, one does the reaction in DMF, which is polar medium water 9:1, then one gets the ratio of 42:58, whereas the same OTF, the same reaction OTF when done in THF, which is non-polar, this is non-polar, and OTF this is polar medium, which is non-polar, then one gets ratio of 8:92. So, one sees the selectivity increases. Similarly, for other anion like PF6 minus in DMF, again it is a polar medium, shows 43 to 57, I minus again in polar medium DMF shows 20 to 80. So, in terms of selectivity, obviously it is seen that the non-polar medium gives rise to this trans product in higher selectivity, and we had seen how the anions get dissociated from in the polar medium as opposed to the non-polar medium. And lastly, there is this beautiful example of seeing this beta hydride elimination, which usually takes place after the olefin coordination insertion has taken place, and this is beautifully illustrated by the following compound. So, this is after step 2, that means coordination insertion, then one forms this type of complex PD P and R1 R2 R3 R4. So, this hydrogen is beta, and this is beta dashed, and what one sees that this will go beta elimination to give the product, which would be of this type R3 R4 R1 R2 plus the palladium hydride complex and would undergo the beta dashed elimination to give the following olefin R3 R4 R1 R2 and then along with this. So, this can be easily identified based on which olefin is formed. Once this olefin is characterized, that will give insight and to how this reactivity is governed. So, with that I would like to conclude today's discussion on Hick coupling reactions, and what we had seen that in the beginning we had looked at the mechanistic cycle for the Hick coupling, and what we had observed that this Hick coupling proceeds by 4 elementary steps. First involves it involves palladium 0 palladium 2 couple. The first reaction obviously is this oxidative addition followed by these olefin coordination insertion followed by the beta hydride elimination, and then last step involves the conversion of the palladium hydride species to palladium 0 species. We had also seen that the anions do have a significant impact in these Hick coupling reactions, and we had observed that these anion sort of stay coordinated to the palladium intermediates and keep it anionic, and hence the reaction proceeds as desired. Lastly, what we had also seen that the reaction proceeds slightly by 2 different mechanisms in polar versus non-polar solvents, and in polar solvent the halide palladium halide gets further dissociated and solvent remain coordinated, and also we had observed that in such a scenario the selectivity of the Hick product goes down in polar medium as opposed to non-polar, and one can also look at the pathway in which the beta elimination which happens after this coordination insertion of the olefin, that sort of provides insight into the regiochemistry of the Hick coupling reaction. So, with this we have done a full circle on the Hick coupling, started from its the scope of the reaction to looking at its catalytic cycle, the mechanism, and then try to understand the different product it produced under different conditions to sort of get a idea on the depth and the breadth of this fantastic coupling reaction. So, I can thank you for patiently listening to me in this lecture, and we are going to take up another very interesting cross coupling reaction, the again the Nobel Prize award winning Suzuki coupling, the much awaited Suzuki coupling in the next lecture, and I look forward to being with you to take up Suzuki coupling in more details, or introduce Suzuki coupling and discuss in details in the next lecture. Till then, goodbye and thank you.